Hey guys, in this tutorial we're just going to go through a simple transformer classification task. So we're just going to build a transformer from scratch and we're going to train it on the IMDb sentiment dataset just to get an idea of what transformer really is. So we're just going to go through the simple transformer layout, the simple architecture. So first things first, we have a sequence, and this is basically your sentence. So suppose I have the sentence "I love this movie," then each of these tokens represent each of this word. And you also notice that we have this extra token here, the CLS token, which is appended to the start of the sequence, and basically this CLS token will capture the entire meaning of the sentence, and we go through it later. Each of these tokens will then have its own embedding. Embeddings are basically your vectors for each of the word. They can help you learn the semantic meaning and between each of these words, and obviously the larger the embedding, the better. And self-attention layer to learn, so each word can understand the context of each other words better and basically understand the meaning of the sentence. And then each of these output will result in an output for each of the token, which can be passed through the feed-forward layer, which can be used to actually classify. So in this case, we're using the CLS token to actually get the output. We pass it through the softmax layer to get our probabilities, and we use that for classification. Okay, so first things first, we're going to start with the tokenizing and embedding process. So let's say we have a simple sentence, "I love this movie." So we just have a batch size of 1 and a sequence length of 4. So after this tokenization is done, we get "I love this movie" in an array. So "I love this movie," and then we create embeddings for each word. So after the tokenization process, we have word indexes for each of these words. So 1 represents "I," 0 represents "love," 2 represents this, and 3 represents "movie." This tokenization process is basically under the hood can be done manually or using libraries such as sklearn, and that's beyond the scope of the video. But basically, each of these index represents the word, and once you have each of these word, we can then put an embedding for each of these words. So "I" can be represented as a vector of 3. So this entire vector represents "I." And then "love" can be represented as the second element here. This can be represented as the third, and so on. Movie is the fourth. So embeddings basically help us to capture the meanings of the words better. So the larger the embedding, the better, because you're able to capture more meaning. But in this case, we're just going to keep it to a simple tree, so it can actually help to visualize. And after we're done with the embedding, we also have to add positional embeddings to each of these embedding, because transformers do not inherently know the positions of each word. It's not like CNN or RNN or basically other sequential neural networks that may know the positions of the words, but transformers do not. So we have to add positional embeddings as well to each of this, and it's a simple vector as well. So we just add it, and we get our final embeddings that we can pass it on to our self-attention layer. So what is the CLS token? So the CLS token is nothing really special, except it's a trainable parameter that we append to the start of the sentence, and this parameter will essentially, after through the self-attention layer and going through the transformer process, it will help to capture the entire meaning of the sentence. And hence, this CLS token, which have an output, and this size is just arbitrary for now, can be used to pass through our, for example, a feed-forward layer that can help us to actually classify our task. So in this case, we have a size 2 output. This represents either positive, and this could be negative. And this is just for example. It can be as many numbers as you want. You classify dogs breed. They can make it larger as you need. So in this case, since we started off with a sentence length of 4, once we append the CLS token, it becomes from 143 to become 153. So this 5 is essentially the CLS token that's been appended to the start. Okay, so now for the more tricky part, which is going through self-attention. So let's suppose that CLS token has an embedding of 1, 2, and 3. So we're just going to focus on CLS tokens to just get a better understanding of what's going on. So basically self-attention, to basically setups for it, there's going to be 3 components of key, query, and value. So once you have this embedding, we have to multiply by a matrix, weight matrix of WK, WQ, and WV. So this is your key matrix, this is your Q matrix, and this is your value matrix. And since we're starting off with 3, we're going to project this in a linear projection to any size that you determine. So this is like a hyperparameter that you have to tune. So in this case, we just set it to 8 for visualization. So we're starting off with a size 3, and then we're going to multiply it by, let's say, hidden size 8. So this matrix size is going to be 3 times 8. And this is going to result in a size 8 matrix, size 8 vector. So we're going to project this size 3 embedding to a size 8 key matrix here. Key vector. Then you have a corresponding query vector and your value vector. So this key, query, and value is going to be done for every single token. And the reason why we do this is for self-intention. We want to learn about each other words and to understand the context better. So how do we do that? Let's start with the CLS token again. So example, we have this query vector that we resulted from here, from X multiplied with the weight matrix of Q to get a vector size of 8. This query vector is then dot producted with every other key vector in the sentence, including itself. So query of CLS is multiplied dot producted with the key of CLS, key of I, key of love, key and this, and movie that's it can be put on the screen. So there's 4 of this dot products, and each of these dot products then create basically a scalar value. It's just a simple dot product. So let's just look at this. For CLS token, this results in a size 5 vector. So it could be like 1, 2, 3, 4, 5. So just for the CLS token, after you do this process of multiplying your query with each other keys, you're going to result in a size 5 vector. Which is why when we do this for every other token, we're going to result in a size of 1, 5, and 5. Because after you're done multiplying query from CLS with every other key, we also have to do the same for query of I with every other key of the sentence. Same for query of love, query of this. And hence, we can quickly do this via a matrix multiplication of query with the transpose of the key matrix. So recall that the query matrix was a size 5 times 8, and the transpose of key is going to be 8 and 5. So when you do this matrix multiplication, you're going to get 5 and 5. And why does this make sense? Remember, just looking at CLS, the query dot producted with every other key is going to result in a size 5 vector, right? And we do this for every other 5 tokens. So we're going to result in this matrix of when we do the Q cross multiply with the transpose of K. So what does this mean? This is the dot product resulting for CLS, dot product resulting for I, love, and this movie, and so on. So what do they actually mean? So why do we actually multiply? When we multiply and get this, for example, for CLS, this gives us our attention scores. And then we have to normalize it and softmax it to get our attention weights. And these attention weights will be then used later to multiply with V to get a weighted sum of V. Okay, so when we multiply with V to get a weighted sum of V, we're going to get back our size vector of 8. So we're going to get 0.4234 and all the way up to size 8 vector here, which basically represents your weighted sum. And this happens for every other vector as well. And so that, for example, from the CLS perspective, once it understood the context of each other word, and this is its representation of the weighted sum of value, and this is unique for every other token as well. Okay, so that was a bit to talk about. So let's just recap everything again. So suppose you have your inputs, and we're going to start with the sentence, I love this movie again. And let's just also append the CLS token here as well. So what you're going to get is a size 5 times your embedding size of, let's say, 3. So basically each of these words has an embedding size of 3, and then we basically add our position encodings as such. And then we go into self-intention layer, which is this part. And we remember each token has a query, key, and value matrix that we have to solve. So since we set our hidden size to be 8, this weight query transpose is going to be a size matrix of 3, 8. Same for key and same for value. So we then multiply with each of these matrix to get our query, key, and value. Okay, so query will equals to, let's just call this X, WQT, and key is the same for WKT, and value is going to be X, WVT. So this tree is a very important formula that we have to remember to get our query, key, and value. So once we do this, we get the entire query will be represented as a 5, 8 matrix. Key is 5, 8, and value is also 5, 8. Nothing too fancy, it just means that each word has a size 8 vector. So basically, each of this word will have its own query key and value that can be used to then cross multiply and then find each of its attention scores and attention weights, which happens in query multiplied by key transpose. If you recall, it's basically going to give you a size sequence length size. Basically meaning, from CLS perspective, for example, this is how I view every other word to give us basically the weights to each other word. So this is going to give us a 5, 5 size matrix that we can then softmax, and then you can normalize it to get our attention scores. Attention scores then can give us the weighted sum that we can cross multiply with the value matrix, which is going to be size 5, 8. So this is 5, 5 to give us back our 158 size vector. So that's all there is to it. So what is CLS exactly? So once we do the CLS token and we get the output for it, in this case we get a size 8 because that's our hidden size that we determine. We can then basically just take this size 8 and you can output a size 2. Okay, so we basically have a linear layer that we can just linearly project it to a size 2 matrix, and this can be represented as, let's say, positive and negative. Okay, and what this basically means is that we can then train it against a sample. Let's say if it's like y values of 0, 1, 0, 1, let's say it's 4, then 0 basically can be negative, 1 can be positive, this can be negative, positive, and then we just train it against the output of this that we'll see later during our implementation.